Yeah. It's a great pleasure to have again the one and only Jesús Guillera, the greatest champions in computing, amazing fast series of pi, who will talk about bilateral rational Ramanujan series and the p-adic mates. As usual, feel free to interrupt every second, but otherwise, please mute yourself. Thank you.
Thank you very much. This talk is based in the paper of the Saint Ethel, but in the lecture, I am going to tell some new things that are not in the paper. A note on p-adic series. Here is example 1. The identity above is has sense in the reals. If we replace x with p, a prime, then we have the identity below, and it has no sense in the reals, but has sense in the p-adics, because these congruencies are satisfied. When p equals 2 to p-adic, we have this sum this is equal to -2, replacing p with 2. And these numbers has a representation to the left side. 0, 1, 1, 0, 1, 1, 1, 1, etc. And -2 plus 2 is equal 0. Indeed, we see that it is correct in this representation. Here is a second example. We consider the function above, and it is very easy to prove that square x multiplied by this is equal to this development. Well, if we denote the function s of n, square n multiplied by this summatory, we see that we need this factor square n because the function f has in the denominator when n reach the big N, which is nu p, then we have a square p in the denominator. So we need a square p in the numerator as well. And when we let x equals nu p, then we have that this p-adic identity S nu p equals S nu plus this. And observe that this part of the p-adic expansion is the with the p-adic zeta, and is identical to the development above. The development the development here. Here. But with the p-adic set. To check this is very easy if knowing these supercongruencies of the p-adic set. If we want to go further, we take n as b has increased. We increase n. We check the identity to further terms. This is our second example. And now, we are going to define the rational Ramanujan series. Bueno, the rational Ramanujan series are of this form. Rational Ramanujan series. And moment. And the value of Z is irrational. The values of the A sub K are positive rationals, and he is the discriminant of a certain quadratic field, imaginary or real, which is also an integer. An example of rational Ramanujan series is this one. And it was conjectured by Jean Cuyen and recently proved by Kang Choi Au using the WZ method. And a very important idea is to consider the bilateral Ramanujan series. The bilateral Ramanujan series is extended to the right and to the left. If we define this function in this form, why? Because the bilateral is periodic, but has poles, and this other factor cancels the poles of the bilateral series. And in addition, due to the fact that if S sub k is in the Ramanujan series, 1 minus S sub k also is, this other factor is also periodic. And so if Le function is periodic and holomorphic, so it has a Fourier expansion. And as the function is orders of this, it terminates at k equal m. So we have this equality where the alpha sub k, beta sub k are the coefficients. And the series to the right and to the left will be denoted in this way to the right and in this way to the left. Observe that this identity for the bilateral holds for all the values of x. As the bilateral identity holds for all the values of x, we can use it to get approximations of the m plus 1 values of a sub k, the m values of alpha sub k, and the m values of beta sub k. All we need is to construct a system of 3m plus 1 equations. Unfortunately, as we cannot solve the system in an exact way because infinite series are involved, we only get approximations. So the bilateral series cannot prove the rational values of the coefficients. We will see later that the p-adic method of the bilateral series comes in our help, allowing to obtain the exact values. Unfortunately, we could not prove the p-adic version, and so it is a conjecture for the moment. It is also interesting to see that the series to the left if the values of x that we are taking are very small, then we can ignore this contribution because it tends to zero as the values of x are smaller and smaller. In addition, we can develop the bilateral series in this way. And the series to the left, when we develop the series to the left in powers of x, we see that it is only possible for module x less than 1. And A curious thing is that the value of A, we can conjecture that it is of this form. This form, of this form, where R is a rational number. Archimedean and p-adic. Now we denote S of n, this function, and why we have constructed this function in this way. This part, this part is we have introduced, apart from the summatory, we have introduced this factor because when n equals nu p, the poles of the series are cancelled with this product. And so it's holomorphic. We need the function holomorphic to get a beautiful a better looking aspect of the p-adic. And this other factor is due to the fact that when n reach this n, so nu p, we have p to the m. And so with this factor, we have that this is orders of p 0, says to 0. And in this way, with this definition, we have, well, the Ramanujan series is given in this way. This is Archimedean. And the bilateral series to the left, the development is this. And we conjecture then that the p-adic analog of this multiplied S of nu, and all this is the p-adic analog of this. So we substitute the functions, the L, the Dirichlet L, with the p-adic Dirichlet, and B with the p-adic B, etc. Well, supercongruencies for rational Ramanujan series. Here is a theorem which I am working still in this first part of this theorem. And the function h defined in this way is multiplicative. It's multiplicative module p m plus 1. And in addition, we have this other property. And the proof of this property is easy because the function g in the function g defined defined by this quotient is independent of nu. And it's independent of nu because it is periodic. And why? And then, and we can generalize the Sutherland's conjecture. Sutherland gave these congruencies, but for nu equal 1, and we can, but this is true for all values of nu in 1, 2, etc. And we can observe that this function, as they are equals, module p-tal, is also multiplicative in this module, for this module. And Thou's conjecture is the extended series to the left is given in this way, then we have this p-adic identity, this p-adic supercongruences. And for nu equal 1, we have Thou's conjecture supercongruencies of 2018. But Thou's determine the value of R directly from the identity. And we see that the parallelism between the extended series to the left and this part of the p-adic identity. Well, we are going to see some examples. For this S of n, this factor cancels the poles consider as function of not only for integers, but for all the reals and complex values. What are the poles? The poles are the negative values of n. Now, a ver. Here. With the poles are cancels. This factor is important, and this factor is due because n reach n. We have the Ramanujan series, the extended series to the left, and with the definition. Oh. Okay. The definition above, the p-adic expansion is very simple. It has this form. And Ramanujan series to the left. We see that this is a p-adic analog of the Ramanujan series to the left. And the other part, this one, is very simple. Well, it is interesting to see that we can prove that the expansion is correct by eliminating some of the terms using different values of nu. And we have done this here. For example, Combining SP and S2P, we get this identity of orders cubic P. In a similar way, we have these identities now orders of square of P to the fourth and P to the fifth. And here we have eliminated even the p-adic set, and we have another identities, and we see that this check in an indirect way the p-adic expansion that we have here. Oh. Here. And example 2, in a similar way, we have the parallelism between the extended Ramanujan series to the left and this part of the p-adic expansion, and the parallelism of the evaluation of the Ramanujan series and this part. Because the square pi written with the function gamma comes here with the function with the p-adic gamma, and it's a p-adic gamma to the 4 that equals 1. And here is example 3. Observe that the poles of this, for example, this factor, and n equals minus 1/2. Do we have a pole and this pole cancels with this. And the parallelism of this with this. And the function Ramanujan series, we see the character is 1. Example 4. Example 4, the Boris Gorevich series, and the poles of this cancels with this and this factor, because n, when n reach n. And in this way, the parallelism is very simple. This well, yes. The character is 4. And the parallelism is of this and this. Well, backwards. For from in our next examples, we redefine the function s of n in this way. In this way, and by doing it, we see that Thudelin's conjecture takes this form. Because now we are not using the factor of n to the m. And the symmetric p-adic theorem takes this form. And in next example, using this kind of supercongruencies, we recover the parameters s sub k of the corresponding rational Ramanujan series. Well, we begin showing examples using Thudelin's conjecture generalized. With only Thudelin's conjecture, we could not give these examples because they need different values of nu in order to have congruencies module the same power of prime. And here is our first example. We want to see if there is a series. We want to see if there is a series of the following form. With character 1. Well, indeed, it exists because using the Will-Zylberger method, we prove that A sub 0 is 1, A sub 1 is 8, and A sub 2 is 20. But here, examine the truth of the generalized Zuderlitz conjecture, we have this kind of congruencies, module P to the 5. And and for all the values of n, the congruencies are of the same module. And we can have systems that are easy to solve. For example, taking P equal 11 and U 1, 2, we get a linear system. Module 11 to the 5. Then we let A sub 0 equal T. And from the above equations, we can get this system. Now, module 11 to the 4. And solving the equations, we can solve taking account that the inverse module 11 to the 4 of this number is this one. We obtain that A sub 2 equals this module 11 to the 4, and this is equal to 20t, and this is equal 8t. So the solutions are of the following form. Example 2 is completely similar. Example 3, the same, completely similar. We solve the equations and we arrive to the solution. And now, finally, we give examples using the symmetric p-adic theorem. The advantage is that we have proved this theorem. And here is example 1. In this example, we know here that a sub 0 is 3 and a sub 1 is 40, using the theory of modular forms. But here we will prove it from the theorem, from the supercongruencies. And for that aim, we let, as we know the solution, but we want to prove it using the p-adic identity. We let a sub 0 equals 3t and take a prime, for example, 23, and we get a system. And we can solve this. We simplify by 23. And we have the solutions. A sub 0, 3t, a sub 1, 40t, which is correct. Our second example is this function conjecture by Guillera using the PSLQ algorithm. We can prove it using these supercongruencies. And for doing it, we consider the prime 7 and the a sub 0, 3t, a sub 1, 460t, and a sub 2, 4,340t, and a sub 3, 20,632t. And by doing it, we obtain a system, and from the system, we can determine a sub 4, which is correct. So with the bilateral Ramanujan series, we could obtain the approximations, but not the rational values. And so this is and this is why the p-adic mates are so interesting. I am very grateful to Vadim Sudilin for sharing several important ideas on the p-adics, and very especially for advising me to replace X with P, 2P, 3P in the bilateral set, and not only with P. Thank you very much.
Thank you.
For your question, please tell me the page number.
So this is a fascinating extension to the p-adic domain. So the conjectures that you mentioned of Sudilin, are they still open from 2008? The Sudilin conjectures that you mentioned, are they still open?
If possible, if you write a question.
Okay, sure. With the chat. Okay.
Here below, see if possible.
Yeah.
Or
Okay. Yeah.
somewhere.
The Zudilin conjectures still open.
Are the Zudilin conjectures still open? Well, I think I am in the good way, and I think the bilateral and some knowledge, special knowledge of p-adic identities will be enough to prove them. But I am thinking still in this way. For the moment, I prefer to be prudent and not. I think I have not good proofs of them. I have intuitions.
Good luck. Thank you. Are there other questions to Jesus? You're welcome to use the chat.
But I think I will continue thinking in this. I am working, trying to prove these conjectures.
Good luck. Very interesting conjectures. Thank you. Thanks so much for everybody for coming. Next week we have a talk by AJ Boo. Thank you, Jesus, and good night. It was really interesting, the extension to the p-adic domain.
Thank you.
Thank you. Bye-bye, everybody. Thank you.
Bye.
I hope it's finished. Bye-bye. Please finish this meeting. Thank you.